the cloud chamber. Today I want to talk to you about one of the first particle physics detectors. Now, you're sitting here and multitudes of these subatomic particles are passing through your body. They're so tiny you can't see them even with the best microscope in the world, but they interact with matter. And that's the basis of this device. Now, these pictures and the video footage you're watching were taken from the Science Museum in London, and I had the pleasure of going there and looking at their exhibit and studying it in the summer of 2019. So I'm going to go through a very basic cloud chamber that you could build yourselves for less than €100. So it consists of an insulated base, dry ice, and felt soaked in alcohol. You cover it with a piece of glass and you shine a light source into the side. Now, the alcohol evaporates, and towards the bottom of the device, it's cold. So it actually forms a supersaturated vapor mixing with the air. Cloud chambers only detect particles that have charge. So particles such as electrons, muons, positrons, antimuons, alpha particles, something that can ionize gas. So once these subatomic particles with charge enter the cloud chamber, they ionize the molecules in this area and create ions. So the vapor condenses around these ions, forming cloudy trails. Now, this was invented back in 1911 by C.T.R. Wilson, and he was a physicist who previously had climbed Ben Nevis to investigate some reports of ghosts. And what he found was, because of the mixture of low pressure and cold temperatures on that mountain, that the ghosts were actually clouds that were forming around small nuclei of dust or charges. And that inspired him to make this particle detector. So I'm going to show you the video shortly of what I took at the Science Museum. And I want you, if you're interested, to see what kind of particles are detected. So if you see short, fat tracks, it means that it's most probably this particle here, an alpha particle. Alpha particles are helium nuclei, and they are produced when radioactive substances decay. All around us, there is background radiation at low level, and part of that is these alpha particles. They come from gas when it decays, rocks such as thorium and uranium when they decay. Now, alpha particles are very massive compared to the rest of the ones that you see here. They are also charged +2, and they are strongly ionizing. That's why they don't actually get very far in the cloud chamber. So they produce short, fat tracks. Now, there are some, you'll be able to see some long, straight tracks, and they are also made from some very exciting particles. They're made from either fast electrons or muons. Now, these two particles, they belong into the same group in particle physics. They're leptons, and they're very similar. Apart from the muon has 200 times the mass of an electron. It also doesn't live for very long. It only lives for about 2 microseconds before it decays. And I'm going to talk more about muons later. So you'll see them on the video as long, straight tracks. Now, the other type of charged particle that you may spot are slow electrons. So they make thin zigzag tracks. They may be actually curving, and this is your regular type of electron. It's not as high energy as a fast electron. Fast electrons may be also caused by radioactive substances decaying. So let's go and see the video now. So I'll just share my screen. Okay, so now I'm sharing the video, that I took at the Science Museum. And as you can see, there are many subatomic particles interacting with the device. Oh, a couple of alphas quickly in a row. So to remind you again, short fat tracks are alpha particles, which are mainly due to radioactive decay. Your regular electron, slow moving, is producing these wiggly zigzag curvy tracks, and high energy electrons, or the exotic, heavy, very brief in lifespan muon, are making the long, straight, thinner tracks. So in this particular experiment, there was no magnetic fields across it, but the early physicists could determine the mass of the particles and what charge they were by applying magnetic fields across the apparatus and looking at the radius of curvature and which way the particle actually curved. So I hope you enjoyed that. And I'm now going to explain to you a bit more about the muon. So I'm going to talk to you a little bit now about the muons, the short-lived exotic particles that you could see some of them in that video footage from before. Now, they were discovered in 1937. They are mainly formed when cosmic rays hit the atmosphere of the Earth. Now, cosmic rays come from out of our solar system. They come from outer space. They formed when you have massive cataclysmic events in other parts of the universe and in other parts of the galaxy. One of such event could be a supernova explosion. So at the end of the life of a massive star, it explodes, releasing particles all over the place. And some of these are protons, which are hydrogen nuclei, and alpha particles, which are helium nuclei. Now, hydrogen and helium make up the main components of a star. These are blasted almost at the speed of light in all directions, and some of them end up striking our Earth. So here's an arrow representing one of these cosmic rays striking our Earth. Now, once it strikes the atmosphere, it interacts with particles in the atmosphere, creating a shower, and some muons are actually produced in that shower. So this is where antimatter was first discovered, by the way, in one of these showers. And muons are produced. Now, we can detect muons on the ground. And this is interesting because they're produced very high up in the atmosphere. They only live for about 2 × 10⁻⁶ seconds. That's 2 microseconds. And yet they actually make it down to the ground. And this is kind of a paradox. I'm going to explain how they make it in the next slide. So measurements on the ground of muons confirm special relativity. The time for the muon itself, so its life as it experiences it, is 2 × 10⁻⁶ seconds. We are watching that muon move close to the speed of light. So for us, the actual lifespan of the muon is a lot longer. So muons exhibit this thing called time dilation. And that's why it's really surprising that we can, well, it's not actually surprising, is it? So we detect more muons than you would have thought because of this special relativity. So I'm just going to go through a few calculations to illustrate what I mean. So why do so many muons reach the ground if their life is so short? The answer is because of special relativity. Now, I'm going to do some simple calculations to explain what I mean. Now, first of all, the average time that a muon exists, I'm going to call it T mu, is 2 times 10 to the minus 6 seconds. Now, muons move super fast. They actually move at 99.99% of the speed of light. So they're almost moving at the speed of light, not quite. Now, C is the symbol that I'm going to use for the speed of light. So if relativity didn't exist, if there was no such thing, then I can work out how far a muon could travel in its lifetime. So using this equation, distance is velocity times time. I just multiply the velocity, which is going to be 0.9999 times the speed of light, which is 3 times 10 to the 8, times the time that the muon exists for, 6, and I get about 600 meters. So muons form in the upper regions of the atmosphere, and if there was no relativity, they'd only travel 600 meters. So we would hardly record any muons at the ground, because the ground level is way more than 600 meters away from the formation where muons are formed. Muons are formed higher than Mount Everest, let's say, like in the upper regions of the atmosphere. And Mount Everest is about 10 kilometers high. So let's now use Einstein's theory of special relativity to calculate the time that we see the muon for. So I'm going to call that time of us on Earth, T, E. So E. Okay, now to calculate that, I need to apply an equation for time dilation. So the time dilation, or what the muon, how long the muon exists in my reference frame, is going to be T, the time the muon actually exists, divided by this factor, 1 minus v squared over c squared. Okay, so let's put in the numbers. So 2 times 10 to the minus 6 divided by the square root of 1 minus 0.9999 squared. So the c squareds cancel out. Now that equals 1.4 times 10 to the minus 4 seconds. Okay, and as you can see, the muon in its reference frame, its lifespan is 2 times 10 to the minus 6 seconds. But us on Earth, TE, we see it for 1.4 times 10 to the minus 4 seconds. That's a factor of 100 times longer. What does this mean? So for us, in our reference frame, the muon actually travels a lot further than 600 meters. So let's see what that means. Let's pick green. Right, so using the formula again, speed is distance over time. Rearrange it to make distance a subject of the formula, dt, vt. So we've got the speed of the muon, which is 9999 c speed of light times, which is times, just rub that out, times 3 times 10 to the 8th times time that we have worked out from before, 1.4 times 10 to the minus 4. And that equals 42,000 meters. So that's 42 kilometers. And that's more like it. So now you can see that even though a muon has only got a lifespan of 2 times 10 to the minus 6 seconds, it can actually travel to the ground because of time dilation, because of Einstein's theory of special relativity. So it can travel 42 kilometers, and that's why we have such high levels of muon detection on the ground. Cloud chambers. And we detect many muons every minute in a cloud chamber. And the reason that we detect many muons in a cloud chamber is because of special relativity. So cloud chambers, fairly simple, fairly straightforward to actually build, and a way that we could confirm special relativity in our lab. So if you enjoyed this video, give it a like on YouTube, subscribe to my channel, and if you have any questions, let me know. Thanks for watching. Bye.